Hello. Before I begin, I want you to imagine something. It is early morning. City is wake up. Roads are clean. Public health system are running smoothly. But beneath this normalcy, under the street, inside the dark toxic space, someone is working. A sanitation worker. He cannot see clearly. He cannot breathe confidently. He does not know if the oxygen is sufficient. He does not know if the structure above him is stable. Yet he enters because the city depends on him. The real question is not whether sewer working is dangerous. The real question is why does safety still depend on uncertainty? Solapur Municipal Corporation face a serious challenges. Sanitation workers perform critical public health functions under extremely hazardous conditions, not because it is technical, but because it is human. Because dignity, safety, and life should not be negotiable. We are Team NIRAKARANA and we present the Smart Safety Monitoring and Assistance System, a technology driven, scalable, software centralized safety platform designed specially for sanitation workers of Solapur Municipal Corporation. Our vision is shift from reactive rescue to predictive prevention. Before any worker enters a sewer, our system performs a pre-entry risk assessment. It processes historical sanitation records, contextual environmental input, and municipal data. It generates a dynamic risk score and calculates safe working duration. Entry authorization is digitally controlled based on their evolution. If the risk exceeds defined safety limit, the system blocked entry. This ensures there is no worker enter blindly. But safety does not stop at the prediction. Several environments are dynamic. So, during operation, the system enables continuous environmental monitoring. Portable sensing unit capture gases concentration, oxygen level, and temperature. Live reading are transmitted to the central server in the real time. If any parameter crosses safety thresholds, alerts are generated instantly. Supervisor receives notification immediately and structured emergency responses workflow are activated. Now, let me explain early stage solution architecture. The system is organized into interconnected subsystems that together form a complete framework. The user interface subsystem provides a role-based dashboard for supervisors and an operational interface for workers. It displays risk score, permits, live reading, and alerts. The authentication and access control subsystem manage secure login and role-based authorization to ensure that only verified users can approve or monitor operations. A data acquisitions subsystem collects historical sanitation data, whether inputs and municipal ERP or GIS information for contextual analysis. The AI risk analysis subsystem evaluates hazards level before entry and generate risk score and safe working duration. The IoT monitoring subsystem capture real-time environmental parameter using portable safety unit and transmit them securely to the server. The decisions and alert management subsystem processes risk output and live reading to generate approval, denial, and emergency notifications. The data store and login subsystem maintain credentials, risk results, operational logs, and incident records to ensure transparency and compliance. The integration subsystem connects external municipal system and environmental data source to strengthen predictive accuracy. Now, looking at the subsystem interaction matrix, the user interface sends credentials to the authentication subsystem for validation. Once authenticated, the interface requests risk data and display result. The data acquisitions subsystem sends contextual information to the risk analysis subsystem. The risk analysis subsystem processes input and sends decision signal to the decision and alert subsystem. The IoT monitoring subsystem continuously transmits live environmental data. If any anomaly is detected, alerts are triggered and logged. All result logs and alerts are stored in the database subsystem. This structured interaction ensures coordination between prediction, monitoring, authorization, and accountability. Now, referring to the architecture diagram. The diagram represents a layered intelligent structure. At the top layer, user interact with the system through the dashboard interface, where approvals, risk score, and alerts are displayed. Below that, authorization validates identity and permissions before any operation is performed. The backend server acts as a central communication hub. It contains the user interface risk analysis model, monitoring subsystem, and database. The intelligence layer processes pre-entry risk evaluation and anomaly detection. Parallel to that, the monitoring layer continuously feeds real-time environmental reading into the system. At the foundation lies the data storage layer, which securely maintains credential risk, output logs, and incident records. All layers are interconnected, forming a closed-loop system where prediction, validation, authorization, and logs operates together in a structured and reliable manner. From a technical perspective, the front end is built using modern web technologies with secure session management. The backend manages APIs, communication, and real-time processing. Risk modeling runs in a dedicated analysis environment using established machine learning libraries. Portable sensing device transmits. Technically, it relies to open predictive model and reliable environmental sensing. Economically, it is software dominant with minimal hardware dependency, making it practical for municipal deployment. It is time technology protects them. Our smart safety and assistance system transforms server operation into a predictive, monitored, accountable, and dignified process. Not after an accident, not during a crisis, but before danger begins.